Hello, welcome back to the channel. So in this video, we will discuss a very important problem, a very important question, which is perhaps one of the most popular questions asked in the midterms and finals as well. And the question is basically about taking the derivative of a definite integral. And we'll talk about this theorem. It is basically an extension to the fundamental theorem of calculus that we'll talk about and cover in this video as well. So before we go over this question, I'll write a very important theorem, the extension of the fundamental theorem of calculus theorem, which would be very helpful in order to solve this question. But before doing that, I would highly suggest, if you have not watched the previous video on the fundamental theorem of calculus, I would highly suggest you to first watch that video in order to get full context of the extension of this theorem. So, whenever you have a definite integral which is represented in the form of integral fx dx, and whenever in these type of definite integrals you have those endpoints which are also functions, for example this is g of x and this is h of x, for example, and based on this definite integral, if you have to take the derivative of this definite integral, if you have to take the derivative of this definite integral, we know that we'll get the function after all, right? Because integration is perhaps the opposite of differentiation. So if you differentiate an integral, you'll get the function itself based on the fundamental theorem of calculus. But in order to solve this question, the original expression will be simplified to, you'll first take the upper endpoint and substitute that upper endpoint into the function. So you'll calculate first f of h of x, and then you'll take the derivative of h of x. So you'll write h dash x or d by dx of hx, and then you'll do the same thing for g and subtract that thing. So now you'll have minus, the next term would be f of g of x, similarly as we did in the h of x part, and sideways you'll have the derivative for g of x. Don't worry if this seems to be a bit tricky, we'll do an example, and based on the example you'll totally get the idea of what we are talking about in this expression. And before going over that question, I'll again explain what this expression means. So this expression is based on taking the derivative of an integral for which the endpoints are also functions. And whenever you have to take the derivative of a definite integral whose endpoints are also functions, you basically take the upper endpoint first, substitute that endpoint into f of x, and then calculate this, and then sideways you take the derivative of that upper endpoint, and then you do the same thing for g of x, and then subtract both of those portions. And now based on this expression, let's calculate the answer to the given question that we have. So in this question you have been given the capital F of x, which is the definite integral, and based on this capital F of x, you have to calculate the instantaneous rate of change of f of x with respect to x. So whenever I see this term, the rate of change of f of x with respect to x, I know that I'm dealing with derivatives at this point of time. So if I have to calculate the rate of change of fx with respect to x, that is basically taking the derivative of, taking d by dx of f of x, right? And in this case, our capital F of x is the definite integral. So we'll take the derivative of a definite integral. And in order to calculate this expression, perhaps, you will evaluate this expression, and based on the result of this expression, you'll get the instantaneous rate of change of fx with respect to x. So let's write the function first. Let's write the antiderivative function, which is the capital F of x, in order to solve the question. So we'll start with writing capital F of x, which in this case is capital F of x is equal to integral 7 to x sine of t square dt, right? And now based on this definite integral, let's first identify our little f of x, our h of x and g of x, right? So we'll start with first writing f of x. So in this case, if we check for our little f of x, that is the function which we are calculating the area under the curve for. So the function f of x would be this, right? But since in this case we are taking f of x instead of f of t, that wouldn't change anything. But since we are taking f of x, we'll convert every occurrence of t with x, right? So since this was originally sine t square, but our f of x is in terms of x, so we'll write sine x square, right? So now we have f of x. Now let's write h of x. Since h of x is the upper endpoint, that is x in this case, over here. And similarly, calculating g of x, which is our lower endpoint, over here, and that is 7, right? So now we have all those functions, right? And now in order to calculate the derivative of this function, the derivative of capital F of x, we will use this expression over here. So now let's start doing that. So first of all, in order to calculate the derivative of f of x, you will take f of h of x first. So first of all, what you'll basically do is you'll substitute this value into your function, and that would make sine t square as sine x square, right? And now you take the derivative of this function, because you have to take h dash x as well. So if you take the derivative of, so we'll do the derivative of x in this case, right? And now similarly we'll do the same thing for g of x. Since our g of x is 7, if I substitute 7 into this function, I'll get sine of 7 square. And similarly, you have to take the derivative of g of x. So the derivative of g of x would be d by dx of 7, right? And now if we calculate this expression, we will basically get the instantaneous rate of change of f of x with respect to x. So now let's evaluate this. So sine x square would remain sine x square. D by dx of x will become 1, right? Because I'm taking the derivative of x, so it would be 1. And now sine of 7 square would become sine of 49. D by dx of 7, since 7 is a constant, it would become 0, right? Because the derivative of a constant is 0. And now, further simplifying it down, it would become sine x square, and this component will indeed be 0. So sine x square minus 0 is sine x square. And that is indeed equal to capital F dash x, or d by dx of capital F of x, which is also the instantaneous rate of change of f of x with respect to x. And that is indeed sine x square for this question. So that's it for this video. I hope you understood the concept that we discussed in this video. Don't worry if this seems intimidating. We'll cover one more example in the next video. So stay tuned for that. I hope that when we'll do another question in the next video, you'll get a better idea about the extension of the fundamental theorem of calculus. Feel free to comment down in this video if you have any doubts. Follow the channel in order to get notified about the other videos that I'll be uploading. Stay tuned. Thank you so much for watching. Bye bye. Take care.